So I'm going to start with the talk. The talk is on shifted symplectic geometry. So this is I would say a relatively recent field. It's definitely become popular in the last few years. Um, and it originally, I think, it originally came from the PTVV paper on shifted symplectic structures. There's been more work beforehand on derived geometry beforehand by Toen and Vezzosi, I believe. So the idea is, I guess I'll motivate the ideas a little bit, but I'm mainly going to focus on the linear case. So um, usually the main objects you study when you look at shifted symplectic geometry is going to be on derived stacks, but due to a variety of reasons, both personal and non-personal, I will only focus on the linear case. So we won't be going into drive schemes. So we'll focus on mainly like the linear case, which mainly relies on homological algebra, and I think the majority of people understands homological algebra here. So I think it's more than enough to like highlight the main ideas that we need for this, and hopefully it gives you a kind of a working understanding of how do people think about these things. So first question is, why do this? I would say that the main motivation as to why you'd like to do something like this, or why you even do derived geometry, is at least derived symplectic geometry, is because there's one fact of life, which is something called the Weinstein creed, that everything is a Lagrangian. So if you ever see something around, that's going to be a Lagrangian, okay? But there's I think a bit of a problem if you think of classical symplectic geometry. So how do you do classical symplectic geometry is the following. I'm just going to remind you real quick. A definition, a symplectic manifold. I think the majority of people here understand these concepts quite well. Is a pair m comma omega with m a smooth manifold and omega a non-degenerate closed two form. Okay, that's not so bad. Now, what is a Lagrangian? So this is a symplectic manifold, and Lagrangians live inside symplectic manifolds, and these are submanifolds. So a submanifold L inside M is Lagrangian if the following two conditions are satisfied. If one, I need the dimension of my manifold to be half-dimensional. I'll explain why you want these conditions in a bit. But the dimension of L is half the dimension of M. And the second condition is that the symplectic form, if I restrict it to L, or in other words, I pull back the symplectic form to L, is going to be 0. Okay, so first, because of non-degeneracy of my skew-symmetric 2 form, this means that my manifold has to be even-dimensional. This is a linear algebra exercise for you. And so this is indeed an integer. And you usually want to think of Lagrangians as kind of like choosing a phase space inside your, choosing a configuration space inside your phase space. So M is even dimensional, so it's 2n dimensional. You usually think of this as being like having both the position coordinates and the momentum coordinates locally, and a choice, a Lagrangian is going to be a choice of position coordinates inside your manifold, inside your phase space, sorry. Okay, now I told you at the beginning that everything is a Lagrangian. So in some way, it's something you usually do in symplectic geometry, try to look at Lagrangian intersections. But something we know about smooth manifold theory is that if you intersect submanifolds, you're not going to have a submanifold again. So in that way, the category of symplectic manifold is not a good category, because you don't have fiber products. So intersections are fiber products. So what's the first fix you would think about if you were trying to, in some way, fix the fact that intersection of submanifolds is not a submanifold. What's the next category you'd like to look into? That's a bit too out there. Let's slow it down a little bit. But I think someone said it, stretching a little bit, but it's a category of schemes. If you intersect, the schemes allows for fiber products. So the next best thing you can try to do is maybe work in the category of schemes. I'm not going to get into too heavy scheme theory. Just for motivation's sake, I'll mention it a little bit. But yeah, the intersection of schemes is a scheme, is a fiber product. And let's work with a little example real quick. So let's take the following scheme. So let me use, I'm going to fix some XY plane. So, and let me use some color. So let's take the scheme given by the y-axis. So this is my scheme, which I unfortunately chose the wrong name, but x given by letting x equal to 0, I guess, not that bad of a name. And sorry, is a scheme, yeah. Yeah, so I'm thinking of this as scheme. I'm not thinking the category of varieties. And I'm going to take this other scheme inside as my plane in blue, which is I'm going to call it y, which is a scheme given by y equals to 0. So we can write these as specs. So let me actually be precise about this. So x is equal to the spec of x comma y, and I'm going to mod out x in the first case, and I'm going to take y to be the spec of x comma y, and I'm going to mod out by the ideal y. Okay. So just looking at this picture, what is the intersection of these two? Intersection y. Well, I'm taking the x-axis, I'm intersecting with the y-axis, so I should only have a point, which is the origin, right? So you can, again, this intersection is a fiber product over A2, which if you know a bit of scheme theory, then if you do fiber product of schemes, this is the tensor product of the corresponding algebras for affine schemes. So this is the spec of, we're going to take the tensor product of the first one, x comma y mod x, and I'm going to tensor it over kxy. Sorry if I'm going over this board with kxy mod y. Again, this is because here my map is the inclusion on the plane. And if you just compute this real quick, you'll find that this thing here is equal to spec of kxy mod x comma y, which really is my origin in some way, 0, 0. Or if you want to be precise, it really is the ideal x comma y mod x comma y, like the coset of x comma y. And but here's something funny about the intersection of schemes, is that if I look at the global sections of x intersection y, the global section of the structure sheaf, I'm going to have this whole thing here. It's going to be x comma y mod x comma y, and this thing here is isomorphic to k, and this thing here, this is one-dimensional over k. Okay. I'll point out a pattern. Yeah. So I'm not making you go through a basic exercise for nothing. This is a. Oh, yeah, no. It is. I will point out a pattern about the sections. Yeah. Yeah. A2. Oh, this is my plane. So it's the product of A1 cross A1. spec of kxy. Yeah. I can write them more explicitly. So you have a surjective map x comma y into k xy, and I'm modding out by this ideal, right? So if I apply spec is contravariant, so I'm going to reverse the arrows. I'm going to have spec kxy mod this inside spec of kxy, and this thing here is what I define to be A2. Oh, that's my structure sheaf of, if I write the O sub x for a scheme x, this is my sheaf of regular functions on x. Yeah. Okay, so that's one example of intersection of schemes. Let's do another one just to point out a pattern that I'm trying to get to. So if I do this, and let's take a different scheme. Let's take, where's my red? So we'll keep the blue being the same, y equals to 0. Sorry, x, yeah, y equals to 0. So my y is equal to the x-axis. And I'm going to take my x to be something different. So let's take, and this kind of points out the beauty of scheme theory as to why varieties are not enough in our day-to-day lives. Let's take our x to be the set with this parabola, so y is equal to x squared. And let me be precise about what I really mean. I'm thinking about this as a scheme, so this is really the spec of kxy mod y minus x squared. And this one here, again, is my same. I'm not going to write it again, but y is the same y as before. So let's look at this intersection. If I do, again, just naively, if I intersect these two, I should still have the origin right here. So x intersection y, this should still be, I'm going to write quotation marks here, 0, 0. Let me write it on the other side. This should still be 0, 0. But let's think about scheme theory. We're not just thinking about points here. So this, if I apply my same thing as before, again, intersections are fiber products. So this is x cross A2 k y. And again, fiber products are tensor products. So I'm going to have spec of the tensor product of these two. So I'm going to have k x comma y mod y minus x squared. And I'm going to tensor this over k comma x comma y of kxy mod y. Okay, and again, if you go through this, just do some commutative algebra, you find that this is the same as spec of, so y here gets mapped to 0, and I'm letting 0 equal to x squared. So this is the same as k x, let's be full about what I'm trying to say. I'm going to map y to 0 because of this, and here I'm going to have x squared also equal to 0. So if you look at the prime ideals of these, so it is still, this is a full-on set equality. Is going to be the prime ideal of x comma y, the coset modded by this. Oh yes, you're right. I'm going to assume k equals, the characteristic is equal to 0. Yeah, for these competitions, I don't think they matter. Yeah, for these competitions, it doesn't. Yeah, this is like, I haven't used anything of special about characteristic 0, but for all the talk, I'm going to assume characteristic is 0. I'm not assuming algebraically closed, so this is something you don't really need, but I will assume characteristic 0. Okay. So again, this is still the origin, but if I look at the global sections now, if I look at the global sections of x intersection y, so let me call this x2. Let's keep it x2, 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 just to keep track of what I'm intersecting. Let's call this x1, x1, and x1, just to keep track of which one of the two it is. And if I look at the global sections of this thing, the structure sheaf, then I'm going to get this ring here, because we're having affine schemes. So x comma y mod x squared comma y, which this is isomorphic to just, I'm setting y to 0, so this is really kx mod x squared. And if I look at this as a k vector space, this really is the same. Let me write as k vector spaces, the same as k, and I'm going to add kx, because I'm letting x squared equal to 0. But so this is two-dimensional k vector space. So intersections of schemes is quite nice because it keeps track of multiplicities. Here I have the intersection multiplicity 1. These are just the intersection of two lines. But if I intersect these two, why would I want this to have multiplicity 2 is because if I look at a different line here, for example, I'm intersecting at 2 points. If I look at a line here, I'm intersecting at 2 points. And as I start approaching, I would still like this to somehow intersect at 2 points, somehow. And this is captured by the multiplicity of the intersection. And we notice that schemes do keep track of the multiplicity by the fact that this has 2 dimensions over k. So that's good. Now let's try something wilder. What if, sorry? That'd be great, but I will not do that. I'll do something worse, is I'll do y intersection y. So what would you expect this to be? So let's notice something. This has 2 dimension as a k vector space, but my scheme itself is 0 dimensional. This thing here has dimension 1 as a k vector space, but my scheme is a single point, so it's still 0 dimensional. So what would I want y intersection y to be? What would I like its dimension to be as a scheme? I definitely want global sections to be finite dimensional, but so we notice here that dimension can change of the global sections, but the intersection of the scheme is still the same, 0, 0, 0. So I somehow would like this to have 0 dimension. Exactly. So the way you would go about it in scheme theory and the way you'd go about it in manifold theory is to perturb it. If you perturb it a little bit, then I would have, let me draw it out. Oh man, I should do talks more like this. Like, just go to the grad house beforehand and just. Okay, so I have my y here, and if I perturb it a little bit, it's going to look something like this. So I will still have 0 dimension. That's how you deal with that's how you would deal with this in scheme theory, and how you would deal with this in some way in manifold theory. You can usually perturb submanifold so that you have a transverse intersection and you have something well behaved. But perturbing is not quite nice. So I'm going to tell you now, why you need derived algebraic geometry. Is because if you do derived intersections, then you can actually have this to be 0 dimensional. So let me talk about this. Yeah. So if you have transverse intersection, this allows for if I have 2 submanifolds, x and y, let me write it. Yeah. So let me write it out. Exactly. It's literally like what the picture would like to tell you. No, it just has to generate the whole thing. So yeah, can you see from here? Do you want a new board? It's fine. Okay. So how to fix this? Um, so that's this intersection y is just the same as y, which let me write this dimension is not equal to 0. So how to fix this? Well, one way is this is how you do it in scheme theory is perturb, or you would do it in manifold theory, perturb so that intersection is transverse, which really means, so let me put 2 points. If I have two submanifolds, I'm using X, so let's do A comma B. That's bad. I couldn't come up with better letters, sorry. In X, so let's call these B submanifolds or schemes, then the intersection is transverse, which I'm going to denote by A intersection with this vertical bar B, if the tangent space is T x A plus T x B is equal to the tangent space of the whole thing, X, for every X in the intersection A intersection B. So it really is the picture that I'm trying to give you. If I perturb this to a different line, then if I look at the space, the span of this line plus this line is the whole two-plane. So this is what transverse means. And if you have transverse intersections, then this implies that A intersection B is a submanifold. Okay, so this is how you do it in manifold theory. In scheme theory, this is still a scheme, or like in general, like the intersection of schemes is a scheme, so you don't have to worry too much about this. But in this case, self-intersections, you'd like to perturb it a little bit still. So that's not too good. We want to kind of have a natural fix for all these things. And like I mentioned, the way you fix this is, I'm going to keep this here, is through derived, going to the derived category, or like the homological category of these. Nope. Nope. Yeah, give me a second. Mhm. Yeah. Okay. So, okay, there's two things we're trying to fix here. First is that intersection of sub-objects has to be an object itself. So schemes, intersection of schemes, I want it to be a scheme. Intersection of manifolds, I want them to be as a manifold. I don't have this. And something else is I want in some way that the intersections always to have the same dimension in some way, if this makes sense. So for manifold theory, if we pass to scheme theory, we can fix one of the problems, which is the intersection being object of the same category. But we haven't fixed this other fact that I'd like self-intersections to be still like follow the same pattern that I have beforehand. I'm not sure I understand the question precisely. Yeah, exactly. Yeah. So yeah, the self-intersections do make sense. Both in manifold theory too, right? If you have a intersecting manifold with itself, I still have this thing. But I think even in manifold theory, if you look at like if you do a self-intersection, like if you have these numbers for these things, right? You perturb it a little bit. So that's one way to do it, but you just don't want it to be ad hoc. Yeah. 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 Okay. So, okay. What I was trying to say with this is one way to fix it. but there are other ways to fix it. This is not the way we want it to be. Because again, why you wouldn't want this to be the fix is exactly because what you say. Because like I have cases where I have non-transverse intersections, but I still have like this nice property that sub-objects are still sub-objects. So yeah, you can try to fix it this way. That's one approach, and there's work done with these kind of things. But a different approach is to like not do transfer, not perturb, but rather just go create a new object that kind of just encompasses this whole thing by itself. Yeah. Oh, well, you would have the tensor product of the like it would just be the same thing. You'd have y on the dot. Yeah. So like I said, you'd have the same thing, but even as schemes, you have the same thing as well. Like the global sections. Sorry. Yeah. Exactly. Yeah. So this would have dimension 1. It would still be like the same line. So these are 0, 0, but that would be 1. Yeah. So the way to fix this is to go to look at derived intersections. So, okay, I'm not gonna get into details as to how you do these things, but just to kind of like maybe satisfy the taste or the thirst you have in your mouth right now, is to look at what would happen if I do this self-intersection of y with itself. So I have y, which is k x comma y mod y. Again, intersections of schemes are tensor products, so I would have some sort of tensor product here, again over kxy. And I'm looking at it as with tensor product with itself. So as is, I would just get, again, the same thing. But you can actually work in a different category, the homotopy category, and you would have this new tensor product, which I'm going to denote by an upper L. This comes from the fact that it's some sort of left-derived functor. But I'm just going to tell you what the answer is for this. If you just compute it right away, you would change this to a cochain complex. And I'll tell you what this cochain complex is you would have this new ring, okay, x comma y. And here I'm going to adjoin this new element psi. I'm going to have this in degree -1. I would have this differential d that goes into k xy. This is in degree 0. And my differential is given by d of x equal to 0 equals to d of y. And d of psi is going to map to this thing that I'm trying to get rid of. And this whole thing I'm going to tensor product with this thing. No. This is some derived category things. Yeah. But yeah, it is. I replaced one of these things to a cochain complex, so I have now more room to play with. And in some way, this has to tell me what I'm trying to get rid of. And yeah, it should add some sort of like extra data that allows me to just take self-intersection without any problem. Yes. Yeah, over kxy. Because I'm trying to get this, in some way, this differential has to tell me what I'm trying to get rid of here. So I'm trying to get, exactly. Exactly. Yeah. So that's exactly like the main idea behind all of this machinery is that you want to like encode all of these by looking at the cohomologies of the new complex you get. But yes, that's how you make the map. Yeah, there's a lot. There's more categorical background you need for this, but at the end of the day, that's kind of the philosophical idea you want to do. So that's what I'm saying. Like, there's some more infinite category stuff going in the background. Sometimes you will have some longer coaching complex, but for this one, if you just compute it, you'll have just this. Yeah. And in general, you will want to keep track of more cohomologies of these. Okay. And now if you go through the calculation, what you'll find is if you actually compute this, just put this on each degree, take track of degrees and the corresponding differential you get. I'll get into like tensor product of coaching complexes in a little bit, but just tell you what the answer of this thing here is. You're going to have the following coaching complex. So I'm getting rid of y. So I'm going to have just this. I'm going to have my differential d, k, x, where now my differential goes from, gives me dx equal to 0 equals to d psi. And you can really encompass this as a single complex, as a single thing, single algebra, sorry, where this is going to be k x psi with d psi equal to 0 dx, where this thing here has degree -1, and this has degree 0. Sorry, x has degree 0. They're not different, they're the same. So what I'm doing is I'm keeping track of the same thing, because here d is just mapping everything to 0, right? So I'm just thinking of this as a yeah, we're good? Okay. Yeah. No. Sorry. No, the only, sorry, here everything, this is the only thing in degree -1. All of these are degree 0. So I'm thinking of these as being like the constants in some way. These all have degree 0. X and y have degree 0. Only psi has degree -1. So I'm only adjoining things that, so here I think of all the variables he has degree 0, and I just started joining things in different degrees so that I kind of get the right answer in some way. Hmm. Yeah. Yes. Sorry. No. It's not K of C. So again, everything is happening over this ring here. So I'm thinking of that. Exactly, yes. Yeah. So yeah, just replace that by A if you want, and just keep track of all the A's. And that works. Okay. Yeah, I'm not getting into the details of this, but that's the main idea behind. Okay. Okay, so then if I look at this, where's the eraser? I can make a spec out of this. So once I reach the step, I can look at the spec. Put this here. So the spec, so again, y intersection y. If I interpret it correctly, this should be the spec of kxy mod y, tensor product, derived tensor product of these two. And this thing here is the same as my last thing. So spec kxc with dc equal to 0. Of course, I need to tell you what this spec actually means, but I will not do so, unfortunately, today, but just at least philosophically. And how does this give me the right dimension? Well, if I look at the dimension of this, with bidimensional, I really mean like the Euler characteristic of this chain complex or cochain complex, I'll have the things of degree 0 minus the thing of degree minus 1. Oh, sorry, the number of generators of degree 0 minus the number of generators of degree minus 1. And that's going to give me 1 minus 1. It's going to give me dimension 0. So philosophically, so the virtual dimension of y intersection y will give me 0, which is what I wanted to. Yeah. Okay. No. Okay. You do in some way. Okay. Yeah, you do because of self-intersections mainly. If you look at self-intersections, then intersection in the classical sense is something, and the intersection in the derived sense is a different thing. But if these things intersect nicely, I'm not going to precise what nicely means, then you recover the usual intersection. So if I actually compute this whole thing on this case here, I will recover the classical intersection again. So I am indeed generalizing things and not just making a completely new set of things. Exactly, yes. So in general, when you do this whole thing, you will be looking at the other characteristic of your complex. Okay, so I agree. Okay, so now we have this thing. Now I've convinced you, hopefully, that the derived category is the derived setting is the place we want to look at, and let's try to do symplectic geometry in this setting. Okay, so I'm gonna erase this. Okay, so I will do a quick, I guess, not recollection, in some way a recollection of homological algebra, just to keep track of the notation I want to use. But I am assuming that you guys are aware of these things. Homological algebra. And I believe this last example kind of pointed out why I want to be looking at homological algebra right now. Okay. So I'm going to fix a cochain complex. So I'm only going to be working on cochain complexes, not working on chain complexes. Whatever I write, always think about it as a cochain complex. So let V, D be a cochain complex. And we're going to recall some basic constructions that we can do with cochain complexes. So the first construction is shifting. If I have a natural number, k and z, then I can look at the shift of vk. So we can make a new complex, vk and d sub k. This is the complex. Again, whenever I say complex, I really mean cochain complex, with whose nth degree is v n plus k, and the differential dk is equal to minus 1 to the k of my differential of v. Okay. And again, if I have a morphism, so or a chain map or cochain map between cochain complexes, I can also look at the corresponding shift. So I'm really just shifting everything. Nothing more is happening here. Okay. Here. This is my degree. So remember that a coaching complex is, this thing here is going to be a graded vector space. So I'm going to have a direct sum of different degrees. And by what this means, this is the n plus k degree of V. Okay, so if you think of Derived cohomology, you have degree k, Derived cohomology, degree k plus 1, and so on. So that also forms a cochain complex. Yeah. I would say, that's a good question. So, that's a good question. Okay, so this is what I will say, is that it was something I will define in a little bit, is symmetric products of cochain complexes. And usually I want to keep track of how, this allows me to keep track of the degrees of the elements. So if you look at, for example, like the exterior product of exterior forms, of forms, then when I multiply the two things, I want to have -1 to the degrees. And putting this thing allows me to keep track. If I shift things, if I do, like, say I take my drum complex and I shift it by 1, I kind of want my D to also shift by 1. I don't want to like have a mismatch of degrees in some way. Yeah. I would say the best way to like get a feel of why you want to do this is really compute things. That's what I found, that gives you a good feeling. But that's what I will tell you right now is, yeah, if I have my drawing complex and I want to shift it, I would like to like my D to shift with my complex. Which one? Ah, yes, this is. Okay, so that's one new construction I can make. Huh. Okay, I'm glad I didn't plan to go to derived schemes, because I'm already 1 hour in, and so let's make another one, is a dual. So we're gonna have duals. I'm gonna make this new quotient complex, V star, D star, where I will be dualizing everything, but I need to be careful about degrees. So this is given by, I want the nth degree, or k degree. I'll keep it as k. This is going to be v minus k star, and my d star. I'll give you a picture as to why you want to do this. And this is going to be, has to go from, actually I'll give you the picture right now. So I have my v goes vk minus 1, vk, vk plus 1, so on. I have my d's here. If I dualize everything, I'll have the other way around. vk minus 1 dual, vk dual, okay. But the problem is that now my degrees, if I keep the same number, my degrees is going down now. That's not good, because I want quotient complexes, not chain complexes. So let's put a minus everywhere. If I replace this by minuses, then I am getting a quotient complex. Okay? So that's why I have this minus sign here. And again, my D star has to be induced by just the adjoint of this, just the dual. So I have my D star going from V star k to V star k plus 1. This is the dual of D from V minus k minus 1 into V minus k. Yeah. is better now. Maybe I should use dagger, Maybe physicists were onto something with that. Okay, so this is the dual. Are we okay with this this definition? Okay. So now the last two things I need to define to you before I define you what a shifted symplectic structure is the symmetric product. So I'm going to define this quotient complex sim 2 of V with let me write the sorry. Let me just write this sim 2 of V. So I know that it's this one. Okay, this is in degree K. Degree K, this is going to be equal to the sum of all P plus Q equal to K. And tensor product VP tensor VQ. And I'm gonna, again, I want this to be a symmetric product. So I'm gonna define this product here, a product structure with A, all right, like this, circle B to be equal to -1 to the degree of A times the degree of B tensor A. So this is something called the Koszul sign rule. And the differential, I wanted to respect the usual differential. So D of A to B. So yeah, so just to make sure, what I really mean by this is this mod this relation here, just in case. And I'm going to have dA B plus -1 to the degree of A dB. Are we okay so far? Yes. Yeah. So yeah, just to make sure, what I really mean by this is this whole thing, but I'm going to mod out by this relation here. Okay, so that's that. And now the important one that I really need, this is just to fill up some space, because the one that I really need is the following. Is the wedge product. So we want to kind of in some way anti-symmetrize that thing. So I'm going to define this new one, wedge 2V, and then D wedge 2V. I will start omitting these subscript eventually, but so I want this to be this is really going to be the same as the symmetric algebra of my V. Sorry, but I'm going to shift my V by -1. Shift my V, each V by -1, and then I'm going to shift it back by 2 at the end. So in some way, by taking tensor products of these two, I'm going to have -1, -1, then I'm going to shift it back up by 2. So I'm going to regain again the original degrees, but my product is going to be a tiny bit different. So just in case, so as a complex, it's really this on the dot, and this thing here is going to be the exterior derivative you get from this, which I'm going to shift by using this rule. But since my 2 is even, I'm going to have the same exterior derivative as this part here. But my product looks like this, A wedge B is going to look like -1. Remember that when I do this product, I am looking at the degree inside whatever's in here, but here my V shifted by -1. So I'm going to have the degree in V. I'm going to shift it by -1. So A -1. Same thing with B. B -1. And permute these two. And again, I have to be careful about what my differential is. I'll give you the answer, but again, you just do apply all these rules that I want you to apply. And D wedge to V of A wedge B, I'm going to have minus dA wedge B plus -1 to the A, and then A wedge dB. So this -1 comes from the fact that I'm looking at the differential in this shifted one, and by my shifting thing, I have to multiply my differential by -1. And the fact that I regain here the same degree as I'd like to have, it's really just a computation. You're going to have -1, and you're going to have this -1 from the D. So you're going to have A -1 from just the degree in V -1. But I'm applying a D, which also has a -1 sign, so I'm going to have the +1 again. Okay, so that's that. Okay, this is the basic constructions that I need, the ingredients. Now let's actually get into shifted symplectic geometry. So why would I want to do this? Or how would I want to do this? I told you that I want everything to be derived. And in some way, what derived means, it means that everything, I want to look at things up to homotopies. So that's a black box. Just assume everything is up to homotopies. I have chain complexes, so I have the notion of a homotopy. This is a well-established thing. So when I say that, let's forget about closed. I only want to look at the linear case. Every linear, if I look at a linear vector, a linear symplectic vector space, sorry, a symplectic vector space, this closed condition I don't need. I just need a non-degenerate bilinear, skew-symmetric bilinear form. And I need to replace non-degenerate by something that's homotopic. What does non-degenerate means? Up to homotopies. And you can look at this way, so let me motivate this. Non-degenerate means that I have a diffeomorphism, isomorphism between V and its dual. So now instead of isomorphism, I want it to be a quasi-isomorphism. I'll define what. Are people familiar with what a quasi-isomorphism is of quotient complexes? I'll define it. And same thing for Lagrangians. So there's a different way to describe what a Lagrangian is. So here I'd like this to have something that's homotopic to 0. That's what I would like. If it is 0, I don't want to 0. I want it to be 0 up to homotopy. So I want it to be homotopic to 0. And how do I keep track of this one? Well, this Lagrangian thing really is the same as saying that the following. So I have L, I have V, I have an isomorphism with V dual, and I can project down to L dual and 0. Saying that this is Lagrangian is the same as saying that this is exact, and I want to replace this by homotopy fiber or a cocone of my coaching complex. Black box, we'll get into it in a bit. But yeah, you can actually, sorry. I see. Yeah. Yeah, I think I'm missing something on. So there's a way to describe it as an exact triangle. Give me 1 second. missed an assumption here. Oh, sorry. No, this is fine. No, this is fine. So this is a quotient complex. If I do this and then that, I get 0. Same for all the other ones. This map here is injective, so the kernel. Oh yes, this is no, you're right. Yeah, yes, you're right. Yeah. Oh yes, because it's more. Yes, you're right. Sorry. Yeah, sorry. It should be squiggly line. Yes. Yes, you're right. Yeah. No. You're completely right. Yes. Okay. Okay. So, where's the eraser? Oh, sorry. Yes. Okay. So, let me tell you what what a quasi-isomorphism is. Just to keep, everyone can be on the same track. So just real quick, I guess I need the quasi-isomorphism and homotopy just for completeness sake. So let B dV W dW be quotient complexes. Again, everything is over K, characteristic 0. So a sorry. So let's do, okay, just to make sure everyone knows what a quotient map is. We're okay with that one? Okay, so let's do quasi-isomorphism. Is a quotient map phi from V to W such that the induced map in cohomology, let me write like this, is an isomorphism. So in other words, what I want to, when I say that I want this to become a quasi-isomorphism, I really mean that I want it to be an isomorphism in cohomology. So since I'm turning everything into quotient maps, I can do this. But that's my goal, to turn everything into quotient maps. And the other thing I want is, okay, so that's quasi-isomorphism. And the definition is homotopy. So if I have phi and psi being quotient maps, a homotopy between phi and psi is a quotient map. I'm trying to take care of the degrees because I always know, I never remember if it's like -1. Let's hope for the best. It's going to be V dV. Sorry, let me just write it as V into W. I think it's got to be degree -1. Sorry? Yeah. So it is shifted down -1. Yeah. Oh, yeah. Yeah, so here one down, then differential goes up. Yeah, okay. So yeah, sorry, I always forget which degree I want. So if I do dw eta minus, or I guess let's do eta dv minus dw eta. I want this to be equal to phi minus psi. So note that this means that phi and psi are equal in cohomology, because I'm looking at the kernels of this, so this goes to 0, and this in cohomology is 0, so these induced map in cohomology are the same. Oh, that's, but by this I mean the induced map in cohomology. Yeah, so if you think of this as being like the RAM cohomology, then this would be the pullback of differential forms. Yeah, but usually you use upper star to denote like contravariant functors. So like the induced mapping by contravariant functors. I'm just keeping that same notation. Okay. No, this is just like algebraically, the fact that this is a cochain map means that it commutes with the differential. So it maps closed forms to closed forms and exact forms to exact forms. So this just means that you have a map that descends to cohomology. But yeah, it might not be a pullback. Like pullback doesn't really mean much algebraically. For like if I just have an algebra, this pullback is not really a thing. Yeah, exactly. Exactly. Mhm. Yeah, yeah. In general, like these are going to be just algebras. Like these are going to be like a bunch of algebras in with a differential map, and then you just kind of make sure that everything descends mod boundaries or co-boundaries. Yeah. So let's actually now do symplectic, derived symplectic geometry. Finally, after so much, an hour and 15 minutes, I can finally define. Okay, so again, the main thing is I want to change this isomorphism. So if I want to define what a symplectic structure is in the derived sense, I want to replace this isomorphism by a quasi-isomorphism, which I just defined for you. So let's actually do linear shifted symplectic geometry. So actually, something I wanted to mention about this second paper. The only reason I can do this talk is thanks to this second paper, which they actually compute examples and they start from the linear case, which is the thing you'd like to do. And the way you usually approach symplectic geometry classically is you start with symplectic vector spaces and then upgrade it to manifolds. The way that I learned this machinery originally was from papers by PTV, the original paper by TVV, and some other like derived algebraic geometry stuff, which it's a very complicated machinery. But the fact, the only reason I can give this talk is because someone actually bothered to write something about the simpler linear case, which is just homological algebra. It's actually 2 months ago. It's February, last month. Yeah. Oh, that's 2013, 2014. Yeah, this is like, it's been out for like 10 years now, but it just kind of like took ground in the past 5 years maybe. Before then, I don't knew many people who did this kind of thing. Yeah. but yeah, this last paper like just came out like last month, and it was updated like a few days ago. That's the only reason I can actually give this talk. Okay, so again, let's fix quotient complex. So let V D. So again, I'm going to omit this lower index. Be a quotient complex. I have 2% on my iPad. Let's try to do our best. So definition, what's a shifted symplectic structure? So an n-shifted symplectic structure on V. This is a cochain map. Which I'm going to denote by omega. Again, exactly like you would do in symplectic geometry classically. Goes from the wedge product of V with itself into the field K, but I'm going to shift it by n here because I'm talking about quotient complexes, so I need to make sure I land in the appropriate degree. And like I mentioned, I want to replace my musical isomorphism by a quasi-isomorphism. So such that the map omega beta, omega flat, sorry, yeah, my omega flat from V into V dual shifted by n, which takes something in V and maps it into omega B wedge here. I want this to be a quasi-isomorphism. Okay, and this part here is what I call the non-degenerate condition. This is the non-degeneracy in derived symplectic geometry. Well, it's as good as you can get for derived stuff, right? For quotient complexes, the best you can get really is up to cohomology. So this really gives you that these two are isomorphic. These two complexes give you the exact same cohomology. As like in cohomology, these are isomorphic. Yes, because that's what quasi-isomorphism tell me, right? That I have a quotient map that is an isomorphism in cohomology. Yes. So yeah. So what I want to look at, that's the philosophy of derived geometry, is look at everything up to cohomology. So this has to be the same in cohomology. This is a flat. So in other words, yeah. So there is I'm lowering. So have something with upper index, something contravariant. So upper index, and I'm lowering down to a lower index here. No. So something here has upper index, right? Something here has a lower index. So what this does is it takes something with an upper index and gives me something with a lower index. So that's what I mean by flat, is I take something that has an upper index and I lower it down. Oh, I'm just calling, this is just a name that I'm giving. This is the map that I, because flat, for example, in general relativity, flat is with respect to the metric. If you just write flat is like you have the metric, I'm making explicit that I really mean it's flat using omega. Yeah. Yeah. No. Usually, like if you look classical differential geometry, people sometimes write G flat, just to like denote that I'm lowering with G. Yeah, no problem. Yeah. Yes, exactly. Exactly. Yeah, we'll compute some examples so that it becomes more, I guess, explicit or graspable. Where is it? Okay, I have to download now my notes in on my phone because my iPad is dying, unfortunately. So let me quick export to my phone. I can actually do it. I can actually do it. V as the green part of lambda 2. No, this is the full coaching complex. Yeah. 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 So this really like it keeps track of every degree. So at some degrees I might have a map. So if I look at here, at some degrees I might have a map up to 0, but I am keeping track of every degree what omega is doing. Yes. Yeah. It does increase the complexity by a lot, but the reward is quite big if you just power through. Okay, sorry. Okay, so sorry if now the I'm on my phone while I talk to you. And again, here what this complex means, so just to make sure, Kn really is the complex given by, I'm going to have a bunch of zeros. Sorry, 0. I'm going to have a k here. I'm going to have another 0 here. And here this k is in degree minus n. So if I look at degree n, sorry, if I look at degree minus n, it's going to have n minus n, so that's 0. And that's exactly my k. So I'm thinking of k as k as the okay, any algebra can be looked as a quotient complex by just putting it in degree 0. So I'm going to have this 0. I'm going to have k in degree 0, 0, and so on. And I'm just shifting it by n, which means that this at n and minus n, we're going to have k again. If that makes sense. Okay. Let me erase this because I think that's just right here. Okay. So we're good with that. Just make sure we have the right sign. Okay, I'm just going to continue. I'll let you think about it, William. The first example, which is probably the one you kind of want to see, is the Derived complex. Like how does that, the classical idea, fit in this story? So we're going to fix X to be a closed oriented n-dimensional manifold. And we're going to let V be the Derived complex. And I'm going to shift it. So this has a differential, the Derived differential, which I'm going to write like this. And I'm going to shift this by 1. Now you might ask me, why would I like to do something like this? Well, there's a couple of reasons. Do I still have my, okay, here. Because if I shift it by 1, by plus 1, then I'm going to shift it back to minus 1, so I'm going to have my standard Derived complex. And I'm going to shift it by 2, but that doesn't change the differential, because I have a minus 1 to the k, but k is even in this case because it's 2, so my differential is the same. So I recover the standard Derived complex. And also because I'm shifting by minus 1, remember that my standard degrees will be shifted by minus 1, but since I'm shifting plus 1, again, the standard wedge product will give me the classical thing that I have. So it might seem weird that I'm shifting it by 1, but it's just to make sure that my sign line up to the classical differential forms that I have and the standard rules. Okay. So in this case, we have a shifted symplectic structure. So we have a 2 minus n shifted symplectic structure given by let's do omega of alpha wedge beta. This is going to be the integral over x of alpha wedge beta. So again, why is it 2 minus n? Well, in order to be able to integrate this in a non-trivial manner, I need the sum of the degrees to be equal to n, to be the dimension of my manifold. So let's actually go through this algebra real quick. Just in case, by this wedge product, I really mean a formal wedge product in wedge 2v. So I don't mean the classical wedge product of forms. I really mean this formal wedge product that I defined to you a while ago. But here, this is the classical wedge product. Are we doing all right? I feel like I lost some of you. Okay. So what would I like this to be? So why is this 2 minus n? Well, let's take alpha in omega star x. Again, my v shifts omega by 1, the Riemann complex by 1. Let's take something of degree p in here, which is the same as something in p plus 1 of x. So p plus 1 form. Let's take beta of degree q, which is something in omega q plus 1x. Now, the only way I can integrate this is if these sums give me the dimension of my manifold. So we want p plus 1 plus q plus 1. Let me just write p plus q plus 2 to be equal to n. But this implies that p plus q equals to n minus 2. And remember that p is my actual degree in my cochain complex. So again, because things are shifting kind of the other way around, this implies that I have the minus of this. So I'm going to have 2 minus n. Or if you want, in other words, if you want, I'm going to have v n this is going to map to k. Sorry. Okay. So I'm going to have my k. Sorry, wedge 2 is my degree. So I have p plus q. In order to properly integrate this, I need this to be equal to n minus 2. So I need to map this into k of L in degree n minus 2. And for this to be non-zero, this is going to be k L plus n minus 2. And for this to be non-zero, I need this to be equal to 0. So I need L plus n minus 2 equal to 0, which implies that L is equal to 2 minus n. And L is my shift here. Yeah. Many ways, that's how you do it. Yeah. Okay. So here's the thing. I know that the only way for this to make sense is if this is a top form, so an n form, because my manifold is n-dimensional. Okay, so let's take something in degree p in my v, not in my standard Derived degree, but in my v degree, my complex degree. And I have something in q. I need their form to sum up to n. So I have, if I just replace, I have this. Okay. So now I know that the only way for my omega to make sense is if their total degree in my wedge 2v is n minus 2. We're good with that? Okay. So again, what is a cochain map of this? It maps something of degree p plus q to something of degree p plus q here. They map the same degree to the same degree. So if p plus q is equal to n minus 2, I have something of degree n minus 2 mapping to something of degree n minus 2 here. Something of degree L map to something of degree, no. omega. Oh, because that's a cochain map. A cochain map maps something of this. I assume here this has degree 0. Usually, when you have these things, you assume that. But a cochain map, if I just say cochain map, I really mean something of degree 0. So you have something of some degree to something of the same degree. So if I have something of degree n minus 2, it maps to something here of degree n minus 2. But in order for this to be non-zero, is if I end up having, so I would replace here by L, and I'm already using n for something else, so let's not call it L. N, let's call it L. And if you just do this math, you find that L has to be equal to 2 minus n to actually land in something that's non-zero. Yeah. Okay, so you can be consistent about this part here. The problem if you shift by just a random L is that you also will be shifting the products and you'll be shifting the differential. So if you want to recover the classical, the RAM complex with the exact same rules you usually have, this is the right shift. You can do a different shift, but you will have to be more careful about your differential in wedge 2V and your products. I haven't computed it, but I think you'll get like the classical one up to a sign. So maybe, so you'll have like some plus and minus going around, but you should recover almost the same thing, as long as you're consistent. If you shift by something else, everything else is going to get shifted, but as long as you're consistent, you should be able to recover this exact same theory. Okay? Oh, I'm just telling you, like, this is an example. But so, okay, what I'm trying to say is that the standard drum stuff corresponds to this. Okay, you have to be a bit more careful, because if you actually, okay, so you have to be a bit more careful. If you actually want to think of the RAM complex as like its proper, like, how do I want to say this? As an actual something that gives you something topological on your manifold X, you do have to go to look at Kähler differentials in a derived scheme, and you have to do more work. So this thing here, I'm kind of motivating you enough that why I want to shift by 1 and do all these things. This does not give you classical symplectic geometry back again. You do have, if you want to look classical symplectic geometry like properly as like a form in a space and so on, you do have to look at derived schemes. Yeah. But naively speaking, this is kind of like, for the linear case, this is pretty good and kind of enlightens a lot of the ideas you'd like classically. Does that make sense? Okay. All right, so let's continue. Let's actually compute a proper example that is not just some random stuff that I'm trying to make it fit some framework that I just created for you. Well, I didn't create it, but I just gave you. So let me, let's erase this, since I highly doubt I'll be able to get to Lagrangians just because of time, but hopefully I can do something. Okay, so let's think of a different example. I will kind of gloss over this example a little bit because I don't want to just run you through an exercise in homological algebra, but you can work it out on your own in your free time. And I think it's a pretty good example to kind of get a grasp of these things. So let's think of a complex with a single non-zero term. So we're gonna have 0. Let's take some vector space W here, and let's take 0 again, and 0 here. And let's assume that this is concentrated in degree. I want to call it K. In my notes I wrote it D, but I'm already using D for differential, so that's not, I'm not gonna confuse you more. And this thing here really is the same as considering my vector space as a coaching complex with zeros everywhere else. and I'm going to shift it by minus k. Okay, so let's look at V. If I want to look at what a shifted symplectic structure is in this case, I need to look at V shifted by -1 because I want to build my exterior algebra. And this is going to be W of minus K minus 1, which is the same as W minus K minus 1, which in some way I'm thinking of this as shifting it by here. So my W is going to be here in degree K plus 1. Okay. Are we good so far? Now let's look at the tensor product of this with itself. So V minus 1 tensor V minus 1. This is going to be the same as let me just do it fully. So let's do it a bit diagrammatically. So we're going to have 0. We're going to have W in degree K plus 1, 0. I'm going to tensor this with 0, W again in degree K plus 1, 0, so on. So if I tensor this one with this one, I get 0. This with this I get 0. The only non-zero part is when I tensor these two together. So I'm going to have 0 everywhere. Sorry, let's put dots. I'm going to have 0. I'm going to have here W tensor W and zeros everywhere else. And the degree of where is this concentrated at is K plus 1 plus K plus 1. This is 2K plus 2. So this tensor product here really is W tensor W concentrated in degree minus 2K minus 2. Okay, so we have this. Let me erase this. I don't know if I would have wanted to erase that. Okay, so we have this. And remember, we also need to keep track of our products. So let me 2K plus 2. So let's keep track of our products. We have A. Let me just write it as a tensor. A tensor B has to be equal to minus 1 of this is degree, everything is in degree D because everything else is 0. Sorry, degree K because everything else is 0. So I'm going to have K minus 1 squared, sorry, K plus 1 squared. And B wedge A, sorry, tensor A. And now I look at cases. So if we just look at the cases here, I'm going to have B tensor A if K is odd, and the minus B tensor A if K is even. So in other words, what this means that, sorry, no, I'm getting over my head. You know, I guess this is still factually correct. I skip something else I wanted to look at, but this is factually correct as well. Okay, so let's actually look at this thing. So this is going to be this part here. W minus 2K minus 2. That's my symmetric product. I'm going to shift it up by 2 because that's what my wedge product required. And this thing is going to be W tensor W minus 2K minus 2 plus 2. So it's going to be concentrated in degree 2K. And again, same product rule applies because this only shifts, doesn't change my product. And so what do we get from here is that if I look at this V, I have two cases. If K is odd, then my product is symmetric. So I would have the honest symmetric, the honest symmetric product of W with itself. I guess I'm going to be shifting it to degree minus 2k if k is odd. And if k is even, then I get the minus sign, so I'm going to have the wedge product of w with itself in degree minus 2k if k is even. Okay, so that's that. Now let's look at what a shifted symplectic structure is in this case. Okay. Okay, so let's go back to here. I'm looking at this tensor product. This goes here to degree 2k plus 2. And if I look at my k shifted by n complex, I'm going to have 0. I want my k to land exactly right here and 0 everywhere else. Otherwise, I'm going to have my shifted symplectic structure going to be 0 everywhere. So if omega is an n shifted symplectic structure, then n has to equal to minus 2k minus 2. Sorry, so this is k plus 2, and I have to shift it up by 2. So actually there's, so my k doesn't have to land here, so then the shifted plus 2. So n has to be equal to minus 2k. And so this is the only possibility. And now if you look at, so I'm going to omit some steps, but if you look at the v star n, sorry, and this should be 2k, then by doing all the computations, then non-degeneracy gives a proper isomorphism, an honest isomorphism of W with its dual. I guess I can explain this briefly. Why this happens is because everything else is 0. So non-degeneracy. Sorry. Oh, I thought you were using your hand. Yeah, everything else is 0. So if you look at being isomorphic in cohomology, these are going to be isomorphic, but the cohomology of this complex is going to just be W in degree. Sorry, I have to look at this one here. No, sorry, W itself. In degree k is going to be, the cohomology of this in degree k is going to be just W itself, and of the dual is going to be W dual itself. So being a quasi-isomorphism really means that it's an honest isomorphism it's an honest isomorphism of vector spaces. So you recover the classical notion of a symplectic skew-symmetric non-degenerate bilinear form in vector spaces, depending on the degree, or just a standard like inner product if k is odd. So that's good. That's a good sanity check. And had another example that I don't know if I want to go through. I guess I'll mention it briefly because it is worth. I kind of need it for the next one. So my second example is the following. So we had a one-term Cauchy complex. Let's now look at a two-term Cauchy complex. And I will omit a bunch of computations here, but you can, again, fill all these pretty easily. They're just exercises in homological algebra. So D, I'm going to have this in degree. So let's do D plus 1. My differential is A. My degrees are D and D plus 1. Yeah, the rest is 0, yeah. And I'm also going to assume that this complex is not acyclic. Acyclic means that their cohomologies vanish, and that would be the same as saying that A is an isomorphism. So That's boring. And also, like if it is a cyclic, then the cohomology is 0. So any shifted symplectic structure is non-degenerate because everything is 0. So you just have maps between zeros, and everything is an isomorphism in cohomology because everything is 0. So let's assume this is not a cyclic. So then I'm going to omit some work, but you can compute what the wedge 2v is. So this is going to be 0 everywhere. I'm going to have E tensor E in degree 2D. Then I'm going to have, let me erase this. I do want to use the full thing. That's the bad thing about doing like homological algebra related stuff, because kind of like have to write long sequences a lot of times. So let's do this, F tensor E, and then F tensor F, and then 0. Okay, so let me erase this remaining thing. Okay. Sorry? Does it fit? Yeah, okay, good. Okay, so this is going to be in degree 2D, 2D plus 1, and 2D plus 2. So I'll omit some steps, but so how do you look at shifted symplectic structures in this case? Well, you have 3 choices of where you could put your K. You can put your K here and have a shifted symplectic structure that goes down here. You can put it here if you want, and then zeros everywhere else. So let me put K. So your shifted symplectic structure would go here. It could go here, or it could go here. You have 3 choices, and the remaining ones are zeros. So we can do this. And now we can start looking at cases. What happens if our K is in here? What does it mean to have a minus 2D shifted symplectic structure? Or look at this case. What does it mean to have a minus 2D 2? Yeah, give me a second. Yeah. What was that? Yeah. Yeah, sorry, it was supposed to be plus 2. Or so you can look at what does it mean to have a minus 2D shifted symplectic structure. What does it mean to have a minus 2D minus 2 shifted symplectic structure? And the real interesting case is really this one. What if you have a minus 2D plus 1, minus 2D minus 1 shifted symplectic structure? The reason why these are not particularly interesting is because if you look at the cohomologies, it's pretty much going to correspond to cases where A is injective or surjective. And if you look at the cohomology, it's going to be like the kernel of this mod the image, which is going to be 0. So you're going to be looking at the kernel of A. And if you look at this last case, you're going to have the co-kernel of A. Let me just write you down what the actual answer is for each one for these 2 extreme cases, and we'll work at this one out more explicitly because it's useful for it's the most interesting one. So if n equals to minus 2D, then non-degeneracy, if you compute the whole thing, co-kernel, again, just as a reminder, I'll just leave it there. Co-kernel is going to be equal to 0. You're going to have the kernel of A. This is going to be equal to the co-kernel, or isomorphic to. So this is where you use the non-degeneracy. We're using all of these, but this is the most interesting part. It's going to be the co-kernel of A dual. It's going to be in degree D plus 1. It's going to be in degree D. And if you look at the degree D minus 1, you're going to have that the kernel of A star equal to 0. So all of these are zeros. So that means that V is going to be this thing here is going to be equivalent to ker A minus D. So the only non-trivial part is this one, and it happens in degree D. So having isomorphism in cohomology means that this V is isomorphic to this in the category of quotient complexes. Yeah. Okay, so that's that. Just in case, this also means that your A is surjective, by the way. This comes from the fact that, sorry? Exactly, yeah. So co-kernel being 0, this means that the f mod the image of A is 0. That means that f and the image of A are equal. So A is surjective. Okay, so that's one case. Let me separate these two real quick. And if you could guess a little bit what happens in the other extreme case, you kind of can probably guess what's going to happen if n is equal to minus 2d minus 2. Then you can do the similar calculation. You're going to have kernel of A is 0, so A is injective. Co-kernel of A is going to be isomorphic to the kernel of A dual, and the co-kernel of A dual is 0. So the only interesting part happens here. So just in case this happens in degree same one as before, d plus 1. Oh, yes. Yeah, d, this should be d plus 1 and d minus 1. Okay. So that's the other one. And again, you get A is injective. I have it here in my hand. And finally, the interesting case. So, oh, actually, this is something that I did not confirm myself, but the references said that actually it's an if and only if. Even if you get that A is injective, I guess it makes sense, yes. If A is injective, then actually you get that n has to be equal to this. And if A is surjective, you get that n has to equal, sorry, if n is equal to minus 2d, sorry, no. If A is surjective, you get that n has to equal to minus 2d, yes. Because again, same computation, you can go through the other way around by isomorphism and cohomology. Okay, now the last part, which is the interesting part, is n equals to minus 2d minus 1. So what happens in this case? Let me write it out more explicitly. So this is the middle case. Here, I have 0. I have E tensor E. And I have E tensor F plus F tensor E. And finally, F tensor F. Actually, I don't even need this first part. But here I get 0, K, 0. Okay, and this map here is my omega. And these are just 0 maps. So what does it mean for omega to be a cochain map? It means that, again, what is my differential here, just in case? So let's call it, what did I call it? D. So let's call this, sorry, I just came up with something last minute. Where this thing here, E1 tensor E2, is exactly the thing you'd expect it to be, as long as you're careful with degrees. But you're going to have, well, I guess I gave you the answer at the beginning what this should be. It's going to be d minus d of E1 tensor E2, then plus minus 1 to the degree of E1, which is degree d, and E1 tensor d of E2. Okay, so just to make sure, so okay, so what does it mean for omega to be a chain map? It means that if I go this way, I get something, and if I go this way, I get the same thing, but going this way gives me 0. So this means that omega of partial E1 tensor E2, this thing here has to be equal to 0. And if you just go through the computation, you'll find that this thing here is the same as omega of E1 tensor A E2 plus minus, sorry, this should be a minus 1 to the d omega of E2 tensor A E1. And I wrote it this way because I want to write everything in terms of something in E times A times something in E itself. And so what you can actually show is that omega is fully determined by a map omega tilde from E tensor F into K such that it satisfies this equality. Omega tilde of E1 tensor A E2 is equal to minus 1 to the D omega E2 tensor A E1. So this fully determines omega. And what I'll give you the punchline of doing this whole computation is you find that if E and E are finite dimensional, then omega is non-degenerate. So you write it here. By doing this computation and going through more stuff, omega is non-degenerate if and only if the kernel of A intersected with the kernel of omega tilde flat is equal to 0, where here I guess I didn't define you what omega tilde is. If I do E1, sorry. Oh no, this is fine. No, this is fine. Okay, yeah. So omega. So the flat is the same thing as I defined you before. Just like put it in the first component. So this is non-degenerate if and only if this happens. And so if the dimensions are finite, I do need to put this condition. And this happens. Okay, unfortunately I won't get to do more because of time, but what I will say is that the reason why I wanted to go through this two-term chain complex was for an example that I believe you would find interesting, is that if you look at, if you have a Lie groupoid, you have a associated Lie algebroid, and that you can look at that as a two-term chain complex, quotient complex, by looking at the anchor maps. So you can put one in degree 0, one in degree 1, and you can actually compute through using this what does it mean to have a shifted symplectic structure. And if you actually go through the whole machinery, you can actually realize Poisson manifolds, because Poisson manifolds give you these structures of Lie groupoids and the algebroids, or Lie algebroids, and you can actually realize Poisson manifolds as examples of these things. And same in my case, something that I've been looking at not so long ago was presymplectic manifolds, which also eventually turn out to be examples of shifted symplectic manifolds, or shifted symplectic geometric objects, whatever category you want to put it in, because you can get rise to these structures. So unfortunately, I won't get to cover more, but I guess I'll remind you why we want to do this, just to keep you motivated if you ever want to look at this yourself, is the fact that we care about Lagrangian intersections. And if I properly motivated the beginning enough for you in your brain, is that if I want to properly realize the Weinstein creed that everything is a Lagrangian, then I should be able to intersect Lagrangians, and they should somehow be a Lagrangian in some way. And you can show using this machinery that actually Lagrangian intersections are going to be something called Lagrangian morphisms, which do actually give you the proper structure of a Lagrangian. So I didn't get into that, unfortunately, but this framework does give you the proper setting where you can actually realize this creed of Weinstein, that everything is a Lagrangian. So yeah, I'll leave it here. In this sense, yes. The original sense is unfortunately more complicated, right? If you look at stuff that people do in Floor theory or like homological mirror symmetry. Like you do start making these categories where you're looking at Lagrangian intersections, but it's very complicated. And usually the way you want to deal with these things is by perturbing a little bit. I'm not really sure how does. Oh yeah, but the thing that that was before this came up on the archive. Like the Weinstein Creed happened like back in the. This is like 30 years ago. The Weinstein Creed. This is like came up like 10 years ago. I think yeah, probably. I thought it was like the 80s maybe, but uh, yeah, but yeah. So like this gives you a proper framework to actually realize this dream. But homological mirror symmetry was still before this machinery, right? I do not know how homological mirror symmetry falls into this. I know how 3D mirror symmetry falls into this because this is something that was interesting about a year ago. But homological mirror symmetry specifically, actually, if you look at 3D mirror symmetry, there's this paper, 3D mirror symmetry is mirror symmetry, which kind of realizes using this framework 2D mirror symmetry as being like morphisms in some category you can make, and I guess this kind of gives you. Sorry, I'm just rambling now, but yeah, I think there is a way to also properly make use of the standard like Fukaya category kind of stuff from this framework, just by going like collapsing down to these hom categories. Those are buzzwords if you understand them. If you don't understand them, it's fine. Yeah, actually, that's how I got interested in him because I had a conversation with him, and that's how I got into that project. Never managed to finish the project, but I learned something at least. Any questions? Yeah.
So where do like the connections in the object
No, you do more stuff. So the reason why the PTVV paper was so fundamental. So here's the thing. The thing that I described to you today, you can very easily realize it in affine schemes, like derived affine schemes. You have in an affine scheme you can because again here I consider the k vector spaces, but you can replace k vector spaces by a algebras where a is some k algebra and so on, or a module, sorry, and then a is a k algebra. And so if you look at the at affine schemes, then this is fully determined by the like spec A is fully determined by A, and you can really play this whole game algebraically without any problem. But and you would replace like how you naively do a derived scheme is you have your scheme X, you have your structure sheaf, and you kind of extend the structure sheaf to a complex O X minus 1 and so on. Usually look at the CDGAs of non-positive degrees and so on, and you play the same game that I did for affine stuff. The problem is, how do you glue things? If I start with a bunch of affine things, how do I glue them? And that's what was so fundamental about the PTVV papers, that they actually give you a way to glue things locally to get something global. Not only in the case of schemes, but also in the case of stacks. So it was quite quite big. So yeah, what I was trying to get at is locally, yes, you will end up doing homological algebra, just like for any scheme, what you do locally is just commutative algebra. But there is a way to glue it together to have a global object, and usually, yeah, I don't know if that satisfies your hunger, sort of. Okay. Ah. Kevin, the reason why I decided to also do this talk is because I was looking at lecture 2, I believe it was lecture 1 or 2, and he was rambling about a bunch of stuff. But at some point he mentioned like, oh, like you can think of this. He had this branes, saying like, oh, you can think of this as like some I think in his case was like a -1 shifted Lagrangian, or -1 shift. Yeah, -1 shifted Lagrangian was in that case. I'm pretty sure, and I was like, huh, that's pretty neat. I did not know, because he was using like these other machinery on like Fukaya categories and stuff like that. So It was like in the lecture where he was computing the category of I don't remember what he was computing, but something. I think like the two torus, like algebraic two torus, something like that. Any other questions?